Pluto, once considered a planet and later reclassified as a dwarf planet, remains a subject of fascination and study in the cosmos. Recently, astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought attention to Pluto's orbit, suggesting that it could be on a potential collision course with Neptune. But how is this even possible, and what could the consequences of such an event be? Pluto's orbit around the Sun is unlike that of any other planet. It takes an astonishing 248 years to complete one full revolution, and since its discovery in 1930, it hasn't finished even one full orbit. Pluto's path is also highly elliptical, making it distinct from the nearly circular orbits of the other planets in our solar system. Moreover, Pluto's orbit is tilted at an angle of 17 degrees relative to the ecliptic plane, adding complexity to its motion. Despite this, Pluto's orbit intersects with Neptune's for about 20 years during each of their respective orbits, which raises the question of why they don't collide. The answer lies in the gravitational interactions of other planets. Early astronomers sought to understand Pluto's unusual orbit, noting its eccentric and tilted path. The discovery that Pluto's orbit crosses Neptune's led to the important question of why a collision hasn't occurred. The key reason is the gravitational influence of other planets, which helps keep Pluto on a stable course. This is where the three-body problem comes into play. It involves the complex gravitational interactions between Pluto, Neptune, and the Sun. These interactions are difficult to predict, but they help maintain the stability of Pluto's orbit. One crucial concept is non-synchronous vibration, which means that when Pluto crosses Neptune's orbit, it is about 90 degrees away from Neptune, preventing a collision. Another factor is orbital precession, which refers to the slight upward movement of an object's orbit. In Pluto's case, when it comes close to Neptune or other massive planets, it is positioned far above their orbital plane, which further prevents collisions. Additionally, there is a phenomenon known as the VZK oscillation, named after three researchers who studied the motion of space objects. This oscillation describes how the gravitational pull between three celestial bodies, such as Pluto, Neptune, and the Sun, affects their motion. For Pluto, the VZK oscillation helps explain why its orbit is so erratic near the Sun but still remains stable over long time periods. Despite Pluto's seemingly unpredictable orbit, these various forces, non-synchronous vibration, orbital precession, and the VZK oscillation, ensure that Pluto's path around the Sun remains stable, preventing a crash with Neptune. Mathematical simulations conducted in the 1980s revealed that, although Pluto's orbit might appear unstable over shorter timescales, it remains predictable and stable over long periods. The interactions between Pluto, Neptune, and other giant planets like Jupiter are also key in maintaining this stability. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This special relationship helps keep Pluto's orbit in check, ensuring it doesn't drift too far out of alignment. Thus, while Pluto's orbit is unique and complex, the forces at play in the solar system work together to keep it in a stable path, preventing any potential collisions with Neptune. Pluto's orbit, along with the influence of Saturn and Jupiter, demonstrates how the gravitational forces of massive planets can help maintain the stability of objects like Pluto within our solar system. Studies suggest that Jupiter's immense gravity plays a significant role in ensuring Pluto follows a stable path, keeping it on course for billions of years. This suggests that Neptune, Jupiter, and Saturn may be working in tandem to help Pluto avoid collisions and other disruptions as it moves through space. Without these intricate gravitational interactions, the solar system could be a far more chaotic place. Small bodies like Pluto might collide with other celestial objects or be ejected from their orbits, causing a cascade of consequences for the rest of the system. For Pluto, in particular, concerns have arisen about a potential collision with Neptune in the distant future. Understanding Pluto's orbit is crucial in mitigating such risks. This situation highlights the dynamic nature of our solar system. Pluto's case serves as a reminder that even seemingly unstable orbits can become predictable and stable over long periods through the complex interplay of gravitational forces and orbital mechanics. It also emphasizes the importance of continuous observation and research to better understand our position in the universe. Pluto's orbit is an excellent example of orbital chaos, a concept referring to how a celestial body's orbit can be extremely sensitive to its initial conditions. Even small changes in Pluto's location or velocity could drastically alter its long-term trajectory. Computer simulations have been essential in helping scientists understand how Pluto moves through space. These models use complex mathematics to simulate how Pluto and other objects, like Neptune, influence each other's orbits. By making minor adjustments in the simulations, astronomers can see how small changes affect Pluto's future path. Interestingly, even though Pluto's orbit exhibits chaotic behavior, featuring irregularities like non-synchronous libration and orbital precession, simulations have shown that it can remain relatively stable over vast stretches of time, like billions of years. This means that despite its apparent unpredictability, Pluto's journey around the Sun is not entirely chaotic, and patterns of stability can emerge. Predicting celestial events, especially those involving irregular orbits like Pluto's, is a monumental challenge. The inherent unpredictability of such systems means long-term forecasts are often fraught with uncertainty. While numerical models are invaluable tools for understanding and predicting the future movements of celestial bodies, they rely heavily on the accuracy of initial conditions. A small error or distortion in the data can lead to vastly different outcomes, making precise forecasting a difficult task. Moreover, Pluto's unpredictable orbit serves as a reminder of the ever-changing nature of the universe. Despite our significant progress in understanding space, Pluto's example underscores how limited our knowledge still is. By studying the gravitational influences of giant planets on Pluto's orbit, scientists gain valuable insights into the broader dynamics of the solar system. It shows how each planet's position and gravitational pull can dramatically affect the stability and trajectory of other objects in the system. Despite the complex forces working to stabilize Pluto's orbit, some astrophysicists have raised concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a prominent astrophysicist, has shared his thoughts on this possibility. Known for his role in reclassifying Pluto as a dwarf planet, Tyson offers a unique perspective on the evolving nature of celestial mechanics and the public's interest in the far reaches of space. He sees the reclassification not as a diminishment of Pluto's status, but as a reflection of our growing understanding of the vast array of bodies orbiting the Sun. Tyson's approach to cosmic mechanics is rooted in continuous learning and adaptation. He views the complexities of orbits like Pluto's as evidence of how much more there is to discover in space. Despite his optimism, Tyson's thoughts on Pluto's future orbit suggest that there are still many uncertainties to explore, particularly regarding the possibility of a collision with Neptune. Will Pluto eventually collide with Neptune, or is this just another example of the cosmic chaos in our ever-changing universe? Only time and further research will reveal the answer. In the meantime, we remain deeply intrigued by the mysteries of our own solar system. The potential for a Pluto-Neptune collision raises important questions about the nature of space and reminds us of how much we still have to learn about the universe. A potential collision between Pluto and Neptune raises fascinating questions about the dynamics of the solar system, particularly when considering the vast differences in the characteristics of the two bodies. The possibility of such a crash challenges our understanding of planetary stability, especially given the current relative positions and gravitational influences at play. Pluto is located at the far outer edges of the solar system, far from the major planets, while Neptune, a gas giant, has a strong gravitational field. The implications of a collision between these two bodies would significantly alter our understanding of gravitational interactions and the formation of the solar system. To understand the potential impact of such a collision, it is important to consider the structure and properties of both planets. Pluto, despite being a dwarf planet, is composed of a mix of elements and compounds, most of which exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and its atmosphere consists mostly of nitrogen, methane, and carbon monoxide. In contrast, Neptune is made primarily of hydrogen, helium, and other lighter elements, with a deep and dense atmosphere. A collision between such disparate bodies would likely alter their composition and behavior, possibly creating a highly visible event across vast distances. What makes this scenario particularly intriguing is the role of other planets in the solar system. While Neptune's gravity plays a dominant role in stabilizing Pluto's orbit, other factors are at play as well. Jupiter, the largest planet in the solar system, has a massive gravitational field that helps to stabilize Pluto's orbit, preventing it from drifting too far into Neptune's domain. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic collision between Pluto and Neptune unlikely. The study of Pluto's orbit and its interactions with Neptune reveals the complexity of the solar system's dynamics. Astrophysicists such as Neil deGrasse Tyson and Michio Kaku are not only concerned with the possibility of a collision but also with how other factors, such as the interactions with larger bodies, influence the relationship between Pluto and Neptune. Jupiter's massive gravitational field acts as a protective shield, preventing Pluto from wandering too far into Neptune's orbit. Without this stabilizing influence, Pluto could potentially shift into more erratic paths, increasing the likelihood of a collision with Neptune. Saturn, though often overshadowed by Jupiter's gravitational dominance, still contributes subtle shifts that help maintain the stability of the outer solar system. Together, these two gas giants, along with Neptune, play a crucial role in ensuring that Pluto's orbit remains predictable despite its irregularities. Without their stabilizing forces, the outer solar system could become much more chaotic. The careful balance of gravitational forces across the solar system also underscores the broader implications of planetary formation. Over billions of years, these forces have not only shaped the orbits of smaller bodies like Pluto but have also influenced the overall architecture of the solar system. For example, the migration of gas giants such as Jupiter and Saturn is believed to have played a key role in shaping the orbits of trans-Neptunian objects like Pluto. These migrations may have altered the trajectories of many bodies in the Kuiper belt, contributing to the relative stability observed today. Despite the apparent stability of Pluto's orbit, scientists remain cautious. Numerical simulations and ongoing observations constantly refine our understanding of these dynamics. Even minor changes in the position or velocity of a planet could lead to significant long-term effects. While current models predict that Pluto's orbit will remain stable for billions of years, these models rely on the assumption that no major external forces will interfere. As space observation technology improves, new discoveries may reveal previously overlooked factors that could influence Pluto's future trajectory, further complicating predictions about a potential collision with Neptune. One of the most intriguing aspects of the Pluto-Neptune relationship is the concept of resonance. This resonance, in which Pluto completes 2 orbits around the Sun for every 3 orbits Neptune makes, is a result of gravitational interactions that prevent these two bodies from colliding, despite their overlapping orbits. This delicate balance is a perfect example of how seemingly chaotic systems can achieve stability through gravitational interactions. The future of this relationship remains uncertain, and even a small shift in this finely tuned resonance could have significant consequences for Pluto's orbit, potentially leading to a more dramatic outcome. Astrophysicists also consider the possibility that an external perturbation, whether from a passing star, a close encounter with another planet, or even the gradual movement of Jupiter and Saturn, could disrupt this delicate equilibrium. Such a disturbance could potentially lead to substantial changes in Pluto's orbit over millions of years, increasing the chances of a future collision, although this remains highly improbable. In conclusion, the ongoing study of Pluto and its interaction with Neptune not only highlights the complexities of planetary science but also raises broader questions about the ever-changing nature of our solar system. Each new discovery about Pluto, its orbit, and its potential future brings us closer to understanding the long-term behavior of our solar system, emphasizing the dynamic and unpredictable nature of celestial mechanics.